This is Algebra 1, Term 3, Lesson 5. Today we'll apply what we've learned about inequalities, put it all together, blend in a little bit of function notation, piecewise functions, and we're going to introduce something new today, which is area under a curve. Let's start with the nail polish problem. This is a 3-act task, and it could take an entire class period depending on how much of this you would like to do. So I'm going to go ahead and play the initial video. Now, if you scroll to the bottom of the site, you can click on Implementation Guide, and it will give you lots and lots of information here. Things you might say, things you might do, ways to get them going along with this. Since we have already done our inequalities for several days here, you probably don't need to do all of this, but I did give it all to you just in case you would like to. I have given you a link to copy this handout if you choose to use it. It has a lot of things on it. Let's go through it and see if this is something you might need. This is the original from their site, but I've given you a copy to it. So when you click that, it'll create a copy of this document. And the purpose for this activity, they're given an example of a question that might show up on a test that would be like this example. So basically when they're finished with the 3-act tasks, they recommend doing this next. And then you can go back over why did they use less than or equal to in the inequality, what does the shaded area represent, what's a reasonable solution, why, and then here's a similar problem for them to work. Here's an inequality that was solved correctly and then a question. Here's an inequality solved incorrectly and a question, and then another inequality to solve. So a little bit of mixed practice. You can do all that or just none of that, or you can maybe just pick out 1 or 2 problems from that if you'd like. But I thought that was a nice resource. I wanted to give it all to you. I did schedule this assignment for a full 2 to 3 days, so you could spend an entire day on the 3-act task and just get a lot out of that. The next thing in our list here is a Desmos activity called Point Collector. So this activity is 60 plus minutes, and they even recommend being sure the kids are logged in so they can continue to work on their activity at a later time. I assigned these through my LMS so the kids would access that way and they could go straight back into the assignment to get to it. So I recommend that if you want to do all of this. Having said that, it depends on your students. If they're strong already in graphing and interpreting and finding points for inequalities, you may not need to do so much, or you may need to do every bit of it. So it's really depends on your students. So let's go ahead and take a look at the point collector to get an idea of what it's like. It says you can collect some points and you aim for a high score. So you basically want to collect blue points but not collect red points. So let's see if I do this. Let's see what that's going to be. I have the highest score. It's a 4. So it'll display I've got 1, 2, 3, 4, 5, but see I have a red, so that subtracts one of those. And so that would be my score. And so you're competing against the other kids in the class, and that is the point of the assignment. And so it's like a puzzle. But they are going to have to actually type inequalities in the blank, and I'm not going to give you the answers, but you can look under sample responses for answers to some of these and so on. My kids really enjoyed this activity. I remember doing it. I don't think I didn't stay on this long a whole day. We actually did something else that day. So you can just say, okay, we're going to stop when we get to 10 or 11. There's a challenge at the end at 12, and then 13. This is interesting. I don't know if we've done one of these yet. They actually create their own point collecting task for other kids to try. And so what I would ask my students to do on these challenge type questions is each student should create their own, and you should work one other student's. And you should always try to work a student who has not been worked yet. So if you see someone has already had a person do their task, don't do that task. Go find somebody who's not done the task. If all of the tasks that are available have been done, then choose one, but maybe the one with the lowest number. And then at the end, I'll ask my kids to go back and make sure every student's task has been completed, because we want all these kids to have their tasks. They did all that work. They need to make sure somebody actually does it. So I do try to make sure that kids go through and do the tasks that are available, all of them. So this activity could take you an entire class period, which is why I did 2.5 days, 2 to 3 days. But you could cut this one short. It depends on how your students are doing. So you could have them just skip to 13 if they're doing great and come back. Now the bulk, or I guess the heart of the assignment, is in your slides. And I am introducing something new. This is actually accumulation, which is something that is like a pre-calculus or calculus concept. But the reason I do it is it's very, it's another rich task that lends itself well to many, many applications. So I introduce this here and then I bring it back throughout the course. If you've ever done or seen any of those FRQs that I've been putting out, the free response questions, this concept is throughout those FRQs. More so in Algebra 2 and Geometry, less in Algebra 1, but it does show up. So let's go ahead and take a look at this first question. Now this is a simple review task. The distance traveled is a function of time, t. So Max traveled at 60 miles per hour for a total of 4 hours. Create a table, a graph, and an equation for d of t. So all of this should be done in the Desmos calculator. They could technically do math.new, but I'm hoping they'll do Desmos because it's kind of nice to have it all in one place. Create the table, create a graph, create an equation, and it's the total of 4 hours, so they need to stop at 4. So they could do 0, 1, 2, 3, 4, and then stop there. Could talk about restricting the domain, whether the graph should be continuous or discrete, linear, nonlinear. There's so many concepts right here in this one graph. So again, take your time. Basic stuff should be easy. Hopefully, at this point, they've seen this so many times, but you know what? You're gonna have a few that are still working on this, and that's why we continue to bring it back. Now we're gonna go into something different. This is the same trip, but this time I'm not asking about his distance versus time, but his velocity versus time. So you may need to talk a little bit about the definition of that word. I did put that in the show notes for the students. Velocity is another way of saying rate of change, which is also the speed in this case because it's a positive velocity the whole time. So what would this velocity look like? Well, his velocity never changes. He travels 60 miles per hour the entire 4 hours. So that should give them a clue as to what this should look like. A horizontal line segment, basically, that starts at 0 and stops at 4. And they're going to create a table, graph, and equation for this. This one should be easier because he doesn't go up or down. They don't have to spend a lot of time trying to figure it out. Now I'm giving them another trip. And this is giving us an opportunity to create a piecewise equation to represent this graph, so that we're reviewing that concept. Then they're going to describe this trip in detail. So we would want to talk about the rate of change for each of the pieces and what's going on with Max on this trip. Again, so far they've not done anything different. This is a little different though. This is the same trip. So you may put yours up and say, I want you to look at this graph here, this velocity graph, and then look at this distance time graph. And what do you notice? Well, this is all horizontal line segments. Why are they horizontal? So have them talk about why these little segments would be horizontal and how this represents the exact same trip. We're looking at velocity, not distance in this case. They are asked to write an equation for this function, so it should have 3 pieces, and all the pieces are just numbers, integers, with restricted domains. All right, now we're getting into the new part. I'm asking them to find the area of the shaded regions here. These are rectangles. Use the units in the graph to interpret the meaning for each area. Well, what I do, and I actually put this up on the big whiteboard, is I will actually do this in front of the kids. This is one of the direct instruction things I absolutely do the first time for sure, is I would label the sides of this rectangle, hours on the bottom and miles per hour on the side. And then I would leave it at that. I may not say anything after that, but I would put it on the rectangle and let them talk about it, think about it, and come up with something. But you're basically multiplying those hours times miles per hour. And since miles is over hours, the hours will cancel out. You'll just be left with miles. So this area actually represents the distance that he traveled. And this is a deep thing at this point, but it's actually pretty simple to do. It's just making sure they understand what it's doing, like what it means once they do it. So the area of this rectangle represents the distance traveled on this time interval, and the area of this rectangle is the distance traveled on this time interval. And then you might want to talk about, why is there no rectangle from 2 to 4 hours? Well, if you go back to your distance time graph, what was happening from 2 to 4 hours? Well, he wasn't moving, which means he didn't cover any distance. He stayed at the same distance that whole time. So this is why there is no area in this interval. It's only on the interval 0 to 2 and the interval 4 to 8. Now they're going to interpret a velocity function. So remember, this is a velocity. This is not distance time. So at 0, what is his velocity? What does that mean? At 2, when t is 2, what is the velocity and what does that mean? At 8, what is the velocity and what does that mean? So they're basically writing a number and then interpreting what these numbers mean in this context. Not distance, but velocity, his speed, his rate, what's happening. For this slide, they're going to write a system of inequalities that would have this solution set. They do not have to bound the region and get it to look exactly like that, as long as they have the 3 inequalities. Now find the area of the triangle. Use units in the graph to interpret the meaning of that area. Well, the units are the same. Your bottom of your triangle here, the units are hours. The left side of this triangle here is in miles per hour, so the area is actually the same meaning, but our area is kind of chopped off here because you've got a triangle instead of a rectangle. And then we're going to break it down even further. Instead of doing the whole triangle, let's stop at 3. When the time is 3, let's stop there, and this makes a trapezoid. Find the area of that. What's happening? What do you know? And what does that area represent in this context? And then here they're going to create bounded regions. This was the most challenging because they're going to try to get that shaded in. This one's pretty easy. I think they only need 2 inequalities to do this one. So compared to the ones they were doing in their last assignment, hopefully this one doesn't take them as long to figure out. I did give them a link out so they can click and just use this graph and just type those inequalities in and try to fill in the rectangle. And we don't want it to spill over at all. We want to bound the domains or restrict the domains and the ranges to keep that shading inside that trapezoid. Once they find the area, they're going to tell me what it means. It means pretty much the same thing it meant on the last 2 slides. So that's not new, but we're doing it again. Try to do it at least 2 or 3 times. And then finally, they're going to do this themselves. They're going to create their own distance time function, their velocity time function. They're going to put equations and graphs for both and describe the trip. I do encourage them to go back to slide 4 and 5, because that's where I first gave them a distance time graph and then the corresponding velocity time graph to go with it. So they can use that for inspiration. They can't use that exact same one, of course, but they can use one similar to that. So they could just tweak it a little bit and make their own. So this concludes our inequalities applications. Next up is the first test for term number 3. Y'all have a great day.